So we started discussing gradient descent and stochastic gradient descent, and I had a bit about Adam, a method to adaptively choose your descent rates, and I was considering skipping it, but then when Peter and I, when we designed the exercise for the week, Peter again showed me these learning curves, Adam versus stochastic gradient descent, and it was just so dramatic that I thought, okay, I cannot skip it. Yeah, we have to talk about it. And so that's what we will start with today. So reminder, what is gradient descent? What is stochastic gradient descent? Then look adaptive scheduling of step sizes, Adam in particular, and then we will turn to backpropagation. All right. So we were looking at the optimization problem of neural networks in machine learning. We said that we have a summation over training samples from some batch, and we have the loss between some crew label and our neural network F, which accepts xi as input and has parameters w, and we minimize this over w. And then we had more terms, regularizations and so on, regularizers, which I omit today. And this here we can also abbreviate as the error associated with parameters w given a batch B. Okay, and then in gradient descent, the scheme that we use is we find new parameters at time t by considering the old parameters at times t minus 1, and then taking a magical step size times this gradient. And for the gradient, I'm now here using index t and not t minus 1, and it depends on the parameters. And if it's stochastic, it depends on the batch. And this gradient here is just the partial derivative of this error that we have with respect to the parameters. Good. And then in gradient descent, we have that our batch B is identical to our training set, to the entire training set T. And in stochastic gradient descent, then this batch B here, sorry, script B is a random subset of the full training set. And we were talking about this stochasticity wiggling around the loss surface, and that allows our gradient descent estimate to be nudged out of local minima and find better minima. Okay, and spoiler, we will talk about this in more detail another time, but in textbooks, you often find pictures of the surface around a minimum looking like so, and then there are typical pictures about what does gradient descent versus what does conjugated gradient descent versus what do second order methods do, and what does a stochastic gradient descent do. And this picture for deep and wide neural networks is wrong. Not in terms of what the stochastic gradient descenter does, but minima in deep and wide neural networks, they are not really points, but they are more like a network or in cosmology, people studying the evolution of the early universe, they have they look at this set of filaments, the cosmic web they call it, and it's more like that I imagine the structure of a minimum to look like. And I will give you evidence for that another time. All right, this is gradient descent. And so stochastic gradient descent is better than gradient descent. And then stochastic gradient descent with a bit of memory or momentum is even better. So in SGD with momentum, we have some exponential smoothing. Or if you wish, some exponential forgetting of the gradient. And this works like so. We still have our magic step size, alpha times, and now we don't take the gradient, but we take, the literature often uses m here, and I think that's a mnemonic for mean gradient. Where the mean is taken across the last few iterations. So mean gradient at times t is given by some parameter times the mean gradient at times t minus 1. And this here can be a number in principle between 0 and 1. And in practice, it is often set to something like 0.9. So we take maybe 0.9 times our previous estimate plus 1 minus beta times the gradient at the current time step. So again, this is typically stochastic. We only use a subset of the training set. And if you want a mechanical analogy, then this is like a ball rolling on your parameter surface. So the space is spanned by the parameters W of our neural network. The surface is the loss surface. So we have this ball rolling around the loss surface. And then there is, in addition, this stochastic gradient term. So a little bit of jitter that we add. And the ball, well, maybe ball does not give the right picture, because that sounds like if we start at a high point, it would roll around infinitely, but it doesn't. Yeah, so we have damping in this process here. All right, this is momentum, and now we come to Adam. I'm sure it's an acronym which stands for something. You know, there's probably an adaptive in there somewhere. What it does is it chooses the step size adaptively for each single parameter. And it does so by dividing, or let's say what the aim is, what it wants to do is, so the goal is to increase the step size for parameter dimensions with a small gradient. When we were discussing robust potentials and such, we often had a picture like so. And if you're somewhere out here, you have a gradient, hopefully, but it's really tiny. And so if you don't choose your step size adaptively, you know, you will take a lot of steps before you get anywhere interesting. And this is, of course, why we do use ReLU and a host of other tricks to try and condition the loss surface to not have these flat slopes, but it's difficult to get rid of them completely. And this is why it's interesting to increase the step size for those parameters that have a small gradient. And one way to do so is, so the approach here, the method is to divide the mean gradient by what's called the raw second moment. And the second moment here is computed across the past few iterations. So what is the raw second moment? You know, when we compute the variance, we have the expectation of some random variable x minus the expectation of that random variable squared. And if we omit this expectation here, so if we do not subtract the mean, that's the raw second moment. All right, so in formula, we have W, our parameters at time t are given by parameters at t minus 1 minus magic step size times, and now we have the mean gradient, and we divide it by this raw second moment. So V is probably for variance here. And to prevent division by 0, we add a small constant. And just as we saw previously, the MT, our mean gradient, is given by beta times the mean gradient at times t minus 1 plus 1 minus beta times the gradient at time t. And this beta can again be, for example, around 0.9. And now what's new is that we have this raw second moment. It's not a variance because we don't subtract the mean, but it is called V here. And then we need another parameter. This is gamma times V at times t minus 1 plus 1 minus gamma times the element-wise squared of the gradient. All right, so the gradient is a vector, and here I square it element-wise. And so I get a new vector, and using a different color here. So this operation here is element-wise. So as a result, this thing here is a vector. And that thing was also a vector. And well, that means that this division here is also considered an element-wise operation. so that I get out a vector in the end. Okay, this parameter gamma is normally chosen to be much larger still, so maybe 0.999. So there is a lot of smoothing going on here. Now, imagine that we initialize this. We need still the boundary conditions. So we can say that the mean gradient at times 0 is just 0. And similarly for this raw second moment. And if we initialize with 0, we will incur some bias in the first iterations. Take a moment to think about, what will be. So we have our gradient, and then we have our smoothed version, and during the first iterations, what will this bias look like? Any suggestions? Yeah? Okay, so you were saying that in the first step, if we initialize with 0, then our so-called mean gradient will be much, much smaller than the gradient that we compute at the beginning of our optimization. And this will be even smaller because we smooth even more. It's mitigated by this epsilon here. By the way, this is also an element-wise operation. And so we have bias in the first few iterations. And generally, this bias just means that we start having a gradient that's too small in the beginning. And this is why, so these estimates here are biased towards 0. In the first iterations. And this is why a bias correction is used. So we put a hat here and a hat there, and we define some bias corrected versions. So this m hat of t is mt, and then we again have this, I use blue here for element-wise, and then we have 1 minus the power of beta, so of beta to the tth power. I'm writing this in the funny way here because what I really mean is beta to the tth power, but previously I always had a t superscript just to indicate what iteration we're talking about. So here the t did not mean we take m to the power of t, it said m at iteration number t. But this time I really want to take beta to the tth power, because this is what we have here in the first t iterations. And similarly, there is v hat at times t, which is given by the biased version. And then we again have element-wise division by 1 minus gamma to the tth power. All right, so these are the bias corrected versions. And so far, this looks meaningful but innocent. But this turns out to be hugely successful. And so much so, the paper by now has 200 and some thousand citations. And in the year 2020, this innocent paper Adam was the most cited paper from the past 5 years. Across all of sciences, yeah? Not the most cited paper in machine learning, but the most cited paper on this planet in the past 5 years, okay? That was in 2020. I don't know what in 2021 was the most cited paper, but that's to say that it has been really, really influential. And that's just owing to its success, yeah? So if you look at the error incurred by some algorithm, and if you look at iterations t, then well, you often find that gradient descent is doing okay, and stochastic gradient descent gives you hopefully a better minimum, and then Adam, bam, it just descends much more quickly. Okay, that's often the case. It's not always the case, but it often is. And then there is a so the advantage, pro, is that we often get faster convergence or faster training. And there are a number of issues also. In particular, there is a discussion about whether the minima found so quickly by Adam, whether they're as good. So there has been a discussion whether the minima found offer worse generalization than those from SGD, stochastic gradient descent. And then there have been papers claiming this, and then there have been papers refuting the claim. And I forgot what's the latest on this, but there is this discussion. Then, well, you have more hyperparameters to tune. It's not many more, but still, hyperparameter tuning tends not to be the favorite pastime of intelligent people. And okay, here you have the epsilon and the beta and the gamma, so it's one or two more hyperparameters to tune than you have otherwise. And well, by the way, it treats, as we see in the equation, it treats all parameters independently. And this is normally fine, but we will, in the end of the year, not in the end of the calendar year, and we will, in the end of the semester, look at geometric machine learning and at architectures that reflect the symmetry of the problem. So Marie showed the planet Earth. So we operate on a sphere And if we want to predict, for example, vectorial properties, so where does something point, then we have parameters that are coupled. Yeah? So then the parameters are not independent, and in that case, Adam can give you weird artifacts. And in such cases, it may be better to use a method such as vector Adam. That's a relatively obscure paper. But Manuel Clocco, a master student, also from physics, who's working in machine learning, or he finished his master's thesis actually, he found that paper, and it did make a difference compared to the normal Adam in the application we were looking at the time. All right. This is Adam, and then there is a lot to say about the learning rates itself. So previously, I just had this magic step size alpha here, another hyperparameter. And in general, so this step size alpha, in general, what most people do is to choose this large initially, and smaller later on during the training. And this is where we now really get to this babysitting of training processes. And you can then often see in the learning curves the moment when a parameter, when this was, well, you can see the moments when the step size was changed by just looking at the nature of the learning curves. And there are lively debates about what is the best scheduler. One that finds favor in parts of our lab is this, excuse me, is the so-called cosine schedule, which was developed in Freiburg, by the way, in the lab of Hutter. And the cosine schedule, as the name suggests, says that across time, you start with a large learning rate, and then I'm now looking at the at a shifted cosine. So imagine that this is, part of a cosine. So if I went on, it would be a sinusoid. And at this moment, so here the learning rate has become really small. So we have converged to some local minimum. And then, like in simulated annealing, so annealing is a term from the processing of metal. Yeah. So if you want to create steel that's really hardened, it's typical to have an annealing schedule. So you heat the metal and then you hammer it or something, let it cool, then you heat it again, and so on. And this is what happens here. You then inject energy by increasing, by using a large learning rate again, and decreasing it slowly, and so on. And then there's not only this version, but there's also then the version when the period of this cosine changes over time. So again, many hyperparameters, but if you work on big models that train for days, and if you work on a family of models in which you try different hyperparameters and so on, this kind of tweaking can save you a lot of time. Yeah? So nobody's favorite pastime, but sometimes useful and necessary to optimize. All right, any questions so far? Okay, then we take an early break today, and we continue in 15 minutes with backpropagation.